Hey, good morning, everyone. Welcome and thank you for joining us for our webinar, Beneath the Surface, CO2 and Energy Storage for Net Zero, as part of Net Zero Week, the UK's National Awareness Week. My name is Ailey Dunnett. I'm from the British Geological Survey, and I'll be your host today as we take you beneath the surface to explore the key role the subsurface can play in our journey to net zero. I'm joined by two of my colleagues today, Dr. Maxine Akhurst and Ed Hough. Maxine is a principal geologist at the British Geological Survey with extensive experience in offshore and onshore geological survey, research and modelling, specialising in CO2 storage research since 2008. Ed is the British Geological Survey's energy storage lead, and he's a geologist with over 25 years of involvement in projects relevant to geoenergy in the UK and internationally, including natural gas, hydrogen and compressed air energy research and heat storage in the underground. We'll hear from Maxine first, followed by Ed, and there'll be lots of time for questions at the end. So please submit your questions throughout the presentations through the question and answer function in Zoom. And without any further ado, let's get started. Over to you, Maxine.
Thank you, Ailey. Okay, good morning, everyone. My name is Maxine Akhurst. I'm a geologist at the British Geological Survey, and today I will introduce our presentation on CO2 and energy storage for our net zero ambitions. Next slide, please. My colleague, Ed, and I will review the wide range of UK geological storage resources. We will consider the different types of rock at suitable depths and thicknesses that the UK can use to achieve net zero emissions. We will also look at our wealth of geological resources that can support grid-scale amounts of temporary storage of heat, natural gas, compressed air and hydrogen, and permanent storage of CO2. We will then consider that the UK has a very busy subsurface and seabed, and how we might best make use of our subsurface. So we will need effective planning to make best use of our seabed and geological storage resources. Next slide, please. During today's webinar, we will very briefly review the role of the British Geological Survey. Then we will consider where geological storage features in the UK government strategies. My colleague Ed will review the temporary storage of energy. I will then review UK resources for permanent storage of carbon dioxide. And then finally, the management of UK offshore, subsurface and seabed for net zero emissions. Next slide, please. So first, the role of the BGS. We are a non-departmental public body established in 1835. And our role in public science is that we provide impartial and independent geoscience advice. We provide the National Repository of Data and Knowledge for UK Geoscience. We develop services to make benefit for government, business and the public in the UK. We provide analytical facilities, observatory networks and laboratories, and we deliver UK leadership and make our skills, expertise and knowledge available locally, globally. We undertake research and development in pursuit of these aims. The BGS primarily delivers research products and services in the UK, but we also operate internationally to maximise our impact of our science and develop our global standing of our scientists. Next slide, please. We have already mentioned net zero emissions. So what does that mean? So net zero is achieved where the emissions that we remove as a nation are equal to the emissions we produce. If we remove more emissions than we produce, this is described as net negative emissions. Where sources of emissions are extremely difficult to remove, net negative technologies are needed to balance them out. To achieve net zero, we must reduce the activities that produce CO2, such as burning coal, acid, gas and oil. We must be efficient with the energy that we do use, regardless of the way that it is generated. And we must use low carbon technologies to ensure that the CO2 that we do produce, such as from industrial processes, is not released to the atmosphere. Next slide, please. Now I'd like to review whether geological storage features in current UK government strategies. Next slide, please. So firstly, I'd like to consider the Energy White Paper, Empowering Our Net Zero for Future, which was published in December 2020. The strategy for decarbonisation of UK industry is focused on clusters, that is, those places where there are large point sources emitting carbon dioxide. Around half of UK emissions from manufacturing and refining are concentrated in the 6 clusters shown here. The annual greenhouse gas emissions is measured in equivalent million tonnes of CO2, with the total annual emissions of 35 million tonnes per year from the 6 clusters shown here. However, the close association of the many large point sources will enable effective implementation of low carbon technologies and the economies of scale to reduce the cost per tonne of CO2 stored. The UK ambition in the Energy White Paper is to deliver 4 low carbon clusters by 2040, 2 by the mid-2020s and another 2 by 2030, with at least 1 on power generation sources. The greater ambition is for 1 or more fully net zero clusters by 2040. Next slide, please. The UK Industrial Decarbonisation Strategy was published in 2021, and the decarbonisation activities to achieve net zero are deployment of carbon capture, utilisation and storage on industrial sites in clusters, that is to capture and store approximately 3 million tonnes of carbon dioxide per year from the energy intensive industries by 2030. The government will also support increasing amounts of fuel switching to low carbon sources such as hydrogen during the 2020s. And the government will also support electrification for industry during the 2020s. Next slide, please. The UK Net Zero Strategy was also published in 2021. The activities described in the UK strategy, including technologies that include the use of natural geological storage resources. These include by decarbonising UK power supply by 2035, by including energy storage, gas-fired generation, energy from waste with carbon capture and storage. To scale up production of low carbon fuels, for example, including 5 gigawatts of hydrogen capacity by 2030, and that has recently been increased to 10 gigawatts in a 2023 policy statement. Now, low carbon hydrogen by industrial processes requires CO2 to be a net zero technology because it produces byproduct carbon dioxide. So decarbonisation of industry using CCUS or carbon capture, utilisation and storage is intended to deliver 4 clusters of industry CO2 sources by 2030. And the greenhouse gas removals, 5 million tonnes per year by 2030, including bioenergy with carbon dioxide capture and storage and direct air capture with CCS as net negative technologies. Next slide, please. So geology is also needed for the UK hydrogen strategy. The requirement for the hydrogen strategy is laid out in this document, and it was published in 2021. So hydrogen is a low carbon solution for the UK's transition to net zero emissions. It is a highly versatile replacement for the high carbon fuels which we currently use and can be used in domestic and commercial heating and also in transport. Hydrogen will need to be available where and when it is needed, and geological storage will be able to address the difference between the daily and seasonal variation in demand and also the steady state industrial production or fluctuating supply from renewables. The focus for the BGS subsurface, the focus of the BGS research are for the subsurface storage options in salt caverns and in porous rocks for a future hydrogen infrastructure network. So these are the underground storage in salt caverns, which is an operating technology storing large volumes at low unit cost. The development technology of storage in porous rocks, including depleted gas fields and porous sandstone formations, is a research activity that is currently in progress. Next slide, please. Now I'd like to hand over to my colleague Ed, who will provide an overview and areas of active research in energy storage.
Thanks, Max. My name is Ed Hough, and I lead the energy storage research topic at the British Geological Survey. And I'll be introducing some of the innovative uses of the bedrock and the subsurface that can support net zero targets, using examples of active research currently underway at the British Geological Survey. Next slide, please. Thanks. We've seen that energy storage will be important in supporting government policy regarding decarbonisation. So energy can be stored in different ways and released on different timescales, from seconds to months. For example, technologies such as high power flywheels and capacitors can release energy in seconds of duration time. Between sort of seconds and days is a space that's occupied by battery storage. And then at largest timescales, we have technologies such as pumped hydro, compressed air energy, aquifer thermal energy storage, mine water storage, and hydrogen storage. And these can deploy energy in terms of weeks to seasons. So longer duration energy storage can support the uptake of renewable sources of energy. And these more seasonal discharge technologies have been reviewed in the post note, the UK Parliament Office of Science and Technology, which is illustrated in the picture on the right of the screen. Geological storage is particularly well suited to long duration energy storage, but it does bring into question how we are using the subsurface, because the similar rocks can be used to support different energy storage technologies. So we are working on understanding the best use of the subsurface in terms of providing capacity for energy storage, locations, so where could underground energy storage take place, but also matching capacity and location with supply and demand. Next slide, please. Okay, I thought it'd be useful just to think about explaining how a rock could store energy, or CO2, or air. So one of the most common rock types on Earth are sedimentary rock types, and these are made up of small grains of minerals, and between those mineral grains are naturally occurring spaces or voids or pore spaces. So the image on the right shows our grains in different colors. So these are grains of sandstone, and between them we've dyed the pore space or the space in the rock blue. So energy can be stored in terms of either heat or pressure or chemical energy, such as methane or hydrogen, in the naturally occurring pore spaces in rocks. These rocks have typically large volumes and can give slow but consistent discharge and production rates. Next slide, please. So other rock types, as well as sedimentary rocks, can also be used to support energy storage. And one of these is naturally occurring beds of rock salt. So rock salt is an interesting geological rock. It dissolves, so it can be dissolved in the subsurface. It flows under geological timescales, and this means it can actually heal itself. So it provides a gas-tight environment where voids can be dissolved in the rock salt. So in the UK, caverns can be dissolved in rock salt, and these can be typically 30 to 100 meters high and up to 100 meters in diameter, and up to 1,800 meters below the ground. So we're looking at quite significant void spaces that can be engineered in the subsurface. Elsewhere in the world, rock caverns can be developed that might be up to 800 meters tall and nearly 3 kilometers deep. So these caverns, once developed, can allow the rapid injection and production of energy. Next slide, please. So the first technology I'll introduce is uses sandstones to store and release the heat and cool, naturally heat cool from the subsurface. So the concept is that during summer, and looking at the image on the right-hand side of the slide, during the summer, where there's a need or a demand for cold aquifer waters can be pumped out of aquifers and circulated around buildings and the air conditioning systems of buildings. And the cold water can absorb heat and slowly heat up, and then the warmer water that's produced can then be pumped back into a different part of the aquifer. We might be only looking at a temperature difference of maybe 5–10 degrees centigrade. Now, during winter, the system can be reversed, where there is more of a demand for heat. So heat, the hot water or the warmer water, can then be pumped out of the aquifers, circulated around buildings using heat exchange and heat pumps, and cooler water resulting can then be pumped back into cooler parts of the aquifer. So globally, there are numerous schemes operating at the moment. There are over 3,000 schemes in the Netherlands, but only less than 20 in the UK. So these schemes are suitable for supporting district scale schemes or industrial or leisure sort of sites, such as leisure centres, shopping centres or hospitals. So next slide, please. So I mentioned that the uptake of this technology is fairly low in the UK, with under 20 operational schemes. And we're investigating this with colleagues from Imperial College in London and at University of Manchester to answer some of the research questions that might enable better and quicker uptake in the UK. So we're looking at where in the UK aquifer thermal energy storage may be possible. We're looking at if aquifer energy storage would be possible in areas of significant demand. And we're looking at what some of the geological controls on heat storage and on storage of cool and on leakage from the systems could be. A big question that we're understanding is how close together schemes could be located, and also looking at how stakeholders and the general public might perceive such schemes and whether or not that represents a barrier to their uptake. Next slide, please. Thank you. So new data is required to improve our confidence in some of these novel energy storage technologies. And to enable this, the British Geological Survey is developing a network of 3 field sites for research into geoenergy. We have a site in Cheshire, which is looking at aquifer thermal energy storage in sandstones. We have a site in Glasgow looking into mine water heat. And we have a site in Cardiff looking more at the urban sort of setting for heat storage. We also have improved analytical capability in the shape of core scanners that can characterize large volumes of rock. And the aim is to evaluate the long-term effect of changing the heat character in the subsurface, which can have impacts on the aquifer properties, including the chemistry, the microbiology, and the natural attenuation capacity of the groundwater regime. So these 3 different sites are available to support research and can be included in research programs. And further information is available on the web link below, ukgeos.ac.uk. Next slide, please. So just looking in a bit more detail at our research site in Cheshire, this is the site that's focusing on heat flow in one of the principal sandstone aquifers in the UK, and is aiming to understand better the processes and potential for aquifer thermal energy storage. So the concept here is that we have a series of boreholes which have been drilled into the sandstone, and hot water can be injected, or cold water in fact, can be injected into boreholes and can be monitored by the borehole array around the heat injection boreholes. So we're looking at really at scales of about a small car park. That's the sort of scale that a scheme might have influence over. And we're really interested in understanding whether or not subtle changes in rock affect how the heat is stored, transported and released. We're interested in how far the heat may travel, and we're interested in different flow mechanisms because, for example, if there are fractures in the rock, they may enable heat to flow faster and further in the system. The site also gives us a chance to optimize monitoring strategies to better understand how we can understand and regulate these sorts of systems. Okay, next slide, please. Okay, now let's consider mine water geothermal. So parts of the UK have had a long history of mining, and there's leaving a legacy of disused and collapsed mine workings, and there's potential for these coal workings to provide a source of heat. So our site that we have developed in Glasgow is a series of boreholes that have been drilled into a disused coal mine. And again, these allow us to understand heat flow in a disused mine. So actually it's a very sort of novel experimental facility, and it will help us understand the resource, the amount of heat that a mine might provide, and the way that the heat could be released. It allows us to understand the environmental impacts and again develop these monitoring strategies so we can understand exactly how the heat and the extraction of heat or the input of cool into these systems might be affecting the subsurface. And it also allows us to develop technologies to sort of optimize and enhance mine water geothermal schemes. Obviously, the potential for mine water geothermal is limited to areas of coal mining. So in the UK, we might be looking at areas that have had a legacy of coal mining, such as central and northern England, South Wales, and the Midland Valley of Scotland. But there are other smaller coal fields dotted around certain parts of the UK. Next slide, please. Thanks. So now let's take a look at the potential for hydrogen storage. So there's a lot of interest in the value of hydrogen at the moment to support low carbon ambitions. Hydrogen as an element is an effective energy carrier. It has a higher energy storage density when compared to technologies such as pumped hydro or compressed air energy, but it has an incredibly low mass. So it has a very low mass to volume ratio, which means that for the same volume at the same pressure, hydrogen might only represent 1/4 to 1/3 of the energy stored by methane, for example. So to replace the amount of energy stored by methane, natural gas, we might be looking at a requirement for maybe 3 to 4 times the volume of storage in the subsurface. So hydrogen at the moment is commercially produced through a technology called reformation, and this as a byproduct produces carbon dioxide. However, there's research underway that's looking at the large-scale production of hydrogen via hydrolysis, which would be a carbon neutral route of production. So at the moment, globally, hydrogen is stored in solution mine caverns in just a few places in the world, in parts of the UK and in Texas in the United States. And there is a question whether or not hydrogen could be stored in porous rocks, which would mean it could be stored in many different locations. Initial studies indicate that for the UK, we likely have enough energy storage capacity in terms of hydrogen storage, in terms of either cavern storage or in porous rock storage. And there is a question whether or not those storage locations would be in the right places to support demand. Some of the issues and a review of the state of the art for underground hydrogen storage have been collected in the recently released IEA underground hydrogen storage report, which is available from the link at the base of this slide, and also is illustrated to the right of the slide. Next slide, please. Thanks, Ailey. So the British Geological Survey have been looking into the potential for the storage of hydrogen in porous rocks. The research question we have is really looking at whether or not hydrogen, if pumped into the subsurface, would react at different temperatures and pressures with the bedrock itself. For example, would there be geochemical or microbial reactions that would be triggered by hydrogen storage itself? So the British Geological Survey is a custodian of rock materials for the UK, and we've used some of these, for example, the red sandstones in the picture to the right, in our experiments. And these experiments are forming part of the Industrial Decarbonisation Research and Innovation Centre. And we're working on this project with colleagues from the University of Manchester. So next slide, please. So to approach the research question, we have developed a laboratory capability that exposes what we think might be candidate storage rocks. And we can expose these rocks to a hydrogen-rich environment at elevated temperatures and pressures. So we've used 50 degrees centigrade and 150 bar. So these might be representative of some of the deeper storage conditions that we might anticipate. And our initial indications are that observed changes to any of the rocks that we've tested in terms of either their structure, composition, or the microbial populations they may support are either very minor or could in fact be related to artifacts of the experiments themselves. So we have further studies underway as part of the Industrial Decarbonisation Research and Innovation Centre programme, and these should be reporting at the end of this year. Next slide, please, Ailey. Thanks. So the final technology I'll discuss looks at using compressed air as a store of energy. So this is a technology that can use wind and solar power, so renewable sources of energy, to actually drive compressors that can then increase the air pressure and then store that air in underground solution mine caverns in rock salt. So when air is compressed, it heats up. So this is called the heat of compression. And a good example of this is when you pump up a bike tire, for example, the valve on the bike tire gets warm. So that's heat of compression. Now, this heat of compression can either be stored, or there are a couple of schemes operational in the world at the moment where this heat is released to the atmosphere, it's vented. If the heat can be stored, then the technology can be a much lower carbon technology. So once air is stored at pressure in one of our storage caverns, once energy is required, the air can be released, the pressure can be released, the gas itself needs to be heated up and can be used to drive turbines and provide power. So in some scenarios, this would represent a true zero carbon technology. But again, uptake for this technology is fairly low globally. So next slide, please. Thanks. So we're working with colleagues at the University of Loughborough, University of Leicester and the University of Nottingham. And we're looking at some of the questions, again, that might affect uptake of this technology. So we're looking at how the whole energy system design can be optimized. We're looking at the techno-economic assessment. So under what sort of economic or technical conditions might sort of favor implementation uptake of this technology. We're looking at the thermal management. So if that heat of compression that I mentioned could be actually stored and used later to actually heat the gas up or heat the air up as it's released. We're also considering some of the potential for environmental impacts, and we're looking at resource assessment and mapping. So again, where in the UK might the geology be suitable to support these sorts of technology, and how much energy could be supported by these. Next slide, please, Ailey. Thanks a lot. So by way of conclusion, the UK has got a diverse bedrock at depth suitable to support many innovative low carbon energy technologies. However, in the UK, the rocks are not the same everywhere, and their composition, their depth and thickness will affect their suitability and their ability to host different energy storage schemes. For example, just thinking of the cavern storage, which requires rock salt at suitable depths in the UK, we might be thinking of areas such as Cheshire, Teesside, but also West Lancashire and Dorset. So these are the sorts of areas onshore that might have rock salt at suitable depths and compositions to support these technologies. Offshore, we might be looking at areas such as the East Irish Sea and the Southern North Sea. So yeah, finally, what we can also do is map out some of these areas and get a better understanding of where the halite, where the rock salt may be suitable to store energy in caverns. So looking at the example on the right-hand side of the slide, this is an example from Humberside, and it shows that red areas may be able to store more energy than the yellow areas, just because of the character of the rock salt at depth. And in the grey areas, there's no halite or no rock salt, so there's no potential for energy storage. So all these areas of research that I've spoken about are active areas of research, and we'll be reporting over the next few months to years. So with that, I'll now hand over back to Max, and we can hear about some of the CO2 storage work that the Geological Survey is involved in. Thanks.
Thank you, Ed. I'd now like to consider the research on the permanent geological storage of CO2 and areas of active BGS research. Next slide, please. So in the view of the UK Climate Change Committee, CO2 capture and permanent storage is seen as a necessity, not an option, to the UK achieving its net zero ambitions by 2050. This was published in 2020, and the report is shown here on the right of the slide. So the carbon capture and storage ambition in the UK to achieve the net zero strategy is the annual capture and permanent storage of CO2 of up to 30 million tonnes per year, including 6 million tonnes to decarbonise industry processes by early 2030. The ambition includes at least 50 million tonnes per year by the mid-2030s. The ambition also includes the removal of greenhouse gas from the atmosphere by direct air capture of CO2 and biomass energy, both with carbon capture and storage, of at least 5 million tonnes per year by 2030. So the big question for us is then, does the UK have sufficient CO2 permanent storage capacity to meet this ambition? Next slide, please. So in our role, as the national provider of UK Geoscience, we host, own and develop the UK National CO2 Storage Database, CO2 Stored. The data in the database has detailed information on more than 570 prospective offshore storage units around the UK. The sites are here shown on the map. The centre points are shown by the geographical position as these open circles. The type of store and the capacity are indicated by the colour and the size of the circles respectively. The stores that are shown in brown are depleted hydrocarbon fields, and the stores that are shown in blue are in the saltwater sandstones or saline aquifers that Ed has been discussing. The database contains much detailed information on each, including calculation of theoretical storage capacity. And the database has been the starting point for industry CO2 storage projects. I'd like you to be aware that the CO2 storage has been in operation at 2 sites for more than 2 decades by our near neighbours, Norway. For example, next slide, please. The Sleipner CO2 injection project, shown in this green circle, has been storing 1 million tonnes per year since 1996, so a total of 25 million tonnes, and so a tried and tested technology. Note the geographical distribution of the storage sites, storage units that have been mapped here, and notice that it was very similar to the distribution of the rock salt formations and the porous strata that Ed has been showing you earlier in the presentation. Next slide, please. So here we have seen the map of prospective CO2 storage units around the UK. So what does CO2 stored tell us about the UK CO2 storage resource? Well, I think first of all, we can say that we do have sufficient theoretical storage capacity. The summed UK theoretical capacity is 78,000 million tonnes of CO2, that is 78 gigatons. The pie charts on the left illustrates that the UK capacity is predominantly within saltwater sandstones or saline aquifers, which is shown by this very large blue sector. The pie chart on the right shows that the capacity is mostly within underlying the North Sea, and this is the purple, green, and orange sectors shown on the right-hand pie chart. We can see from this that the capacity that we have it significantly exceeds UK ambition to store between 30 and 50 million tonnes per year. The suitability of porous sandstones and depleted gas fields is also being assessed for hydrogen storage, as we have heard from Ed. So the BGS research considers where and how UK CO2 can be permanently stored for decarbonisation of UK power generation and clusters of industry. So I'd like to review some of the research that is currently underway on the geological formations around the UK, and we will focus in on the southern North Sea, as this is an area that is planned for storage by 2 of the UK industrial clusters. The UK government has undergone a cluster sequencing activity, and 2 of their most forward thoughts are that the Teesside and Humberside industrial clusters are part of their Track 1 cluster that is part of their ongoing support. And so BGS research is looking at the mapping and modelling of CO2 storage in the Bunter Sandstone, which is where the 2 clusters are planning to store their CO2. In this map, on the right-hand side of our slide, we can see the extent of the Bunter Sandstone offshore the eastern coast of England. And in it, we can see zones in the Bunter Sandstone, which are defined by geological faults and structures, shown on this map either in red or black. So BGS are mapping and modelling CO2 storage to investigate whether the boundaries between these zones are open or closed to flow in the subsurface. Next slide, please. So I'd like to look at work undertaken, it's current work undertaken by BGS colleagues. And this is to look at the effect of injection of CO2 and how that has an impact on the pressure within the geological formation. And we are looking at 2 end members here. We are considering if the boundaries are entirely open and the zones are in hydraulic continuity, or whether the other end member that they are closed to flow. So the pressure will determine how much CO2 can be stored and at what rate it can be stored. So if we look at the 2 examples, the image on the left is where there's open to flow. The increase in pressures is relatively low, associated with each of those coloured injection points. On the other hand, if the boundaries are entirely closed to flow, you can see that the increase in pressure, so the CO2 injection is higher, and this is shown where there are brighter colours, and also where there are the circles are shown highlighted by the circles. So where the pressure is increased, there will be less storage capacity and the rate of injection will be lower. Next slide, please. Another of the activities is that BGS, British Geological Survey, and UK Research and Innovation are scoping a UK CO2 storage research facility. This is to support research in terms of site characterisation, injection, monitoring, and post-injection site closure. The science case for the facility comprises knowledge gaps and science challenges that have been identified by our stakeholder community. The knowledge gaps are listed here. These include long-term storage efficiency to improve security and reduce risks and costs. What are the effects of different subsurface geological processes at scale? How the cost-effective monitoring and conformance technologies, environmental research and strategic management, and very importantly, social attitudes to local hosting of a major net zero infrastructure. So the science challenges are the outstanding research questions, the how and what questions. How can we improve efficiency of storage? How much CO2 is trapped by each of those mechanisms? How can we make monitoring more cost effective? And how can we understand social attitudes to net zero infrastructure? And the science case is presented in a publicly available report, downloadable at this address. Next slide, please. So we have seen, by comparing the different maps shown by Ed and myself, there are common areas of suitability for hydrogen storage in salt and sandstones that are suitable for CO2 or hydrogen storage. Now I'd like to review ongoing research on the use of UK geological storage resources for the energy transition in the Managing Offshore Energy Transition, or the MOE project. Next slide, please. So MOE is the UK's first holistic study of the environmental and social impacts resulting from the rapid expansion of offshore infrastructure. And this is driven by the UK's energy transition to net zero emissions. The research is funded by the Natural Environment Research Council and is started in 2022 and is of 5 years duration. The research is conducted by 3 UK research institutes: the British Geological Survey, Plymouth Marine Laboratory, and the National Oceanography Centre in Southampton. Next slide, please. So the research activities are to address the effective and optimal use of the subsurface geological resources for temporary hydrogen and permanent CO2 storage. So these are the characteristics at the bottom of the column shown on the right of our slide. We are also looking at the environmental sustainability of offshore energy infrastructure, also understanding the impact of activities of the shallow subsurface, seeps, and the marine environment. So this is the shallow subsurface and the seabed in the midpoint in our column on the right. Very importantly, the societal consequences of the energy transition. That is the topmost surface in this column, with an important activity to translate our scientific research into stakeholder-led outcomes to support decision-making. Next slide, please. So wherever you look around the UK, the offshore UK is already very busy, both in terms of the seabed and in the subsurface. When considering the transition to low carbon technologies, we have to consider existing activities and also new uses, those new low carbon technologies for net zero. And as we have seen, these include temporary storage of hydrogen in engineered salt caverns, temporary storage of hydrogen in porous strata, the permanent storage of carbon dioxide in porous strata, and the installation at the seabed of offshore wind farms. We also need to consider existing activities such as natural gas production and subsurface storage of natural gas. In our work for the MOE project, we will considering not only the physical interaction of the storage facilities themselves, but their infrastructure, but also their operation. So what is the impact of seasonal storage, so recharge and discharge for hydrogen, and permanent storage for the pressure of injection for carbon dioxide. So in our project, we will be addressing the synergies and also how we can minimize conflicts of subsurface and seabed use. Next slide, please. So we have seen earlier that the UK industrial decarbonisation is are in industry clusters. And these are also the focus for the MOE research. And this has helped us to define 3 areas of interest. In the industrial cluster sequencing event are the track 1 industry clusters. And these are Humberside and Teesside in the southern North Sea. So that is our area 1 to the east of the UK. Hynet in the Liverpool Bay area, so our area 2 to the west of the UK. And the reserve cluster, which is Akhurst in Scotland, so our area 2 in the northeast of the UK. Our initial work has been in area 1, and we have been investigating the subsurface and the seabed for its low carbon technology uses. And the importance is that the activities are fully integrated to enable us to consider the synergies and to minimize conflicts of use. Next slide, please. I think one of the challenges of the energy transition to me is evident in the mapping of store strata in the southern North Sea. And here we are offshore Teesside and Humberside in this map. The proposed and consented wind farms are shown in blue and purple. The prospective CO2 storage units are shown in pink. The proposed and consented CO2 storage license areas are shown in shades of green. Their extents at the seabed or different depths below it show very clear overlap. So the mapping of sites for CO2 storage is in salt caverns, CO2 and hydrogen storage in porous rocks is in progress, and we are modelling of the storage operations to inform management to address synergies and minimise conflicts of use. So I'd like then to move my last slide. So we have seen in our presentation today that the UK has a very wide range of natural geological storage resources. The variety of UK bedrock types at suitable depths and thicknesses can support our progress to achieve net zero. Our geological resources can store a variety of technologies and store grid scale amounts of heat, of natural gas, compressed air, hydrogen, and impermanent storage of carbon dioxide. We have seen that the UK has a very busy offshore subsurface and seabed, and that there are overlapping geological storage resources and seabed wind farms. And we will need to have effective plans of subsurface and seabed use to ensure the best use of UK natural geological resources. Next slide, please. So thank you very much for your attention. We will be pleased to answer questions. Do put your questions using the webinar Q&A facility. Thank you very much.
Okay, thank you, Maxine and Ed. So we have a few questions to get us started, but if you have any more questions, we've got plenty of time to answer them. So please do put them into the Q&A function. So I'll start off with a question for Ed. This question comes from Simon. Which fluid would you use to store energy underground? And what is your opinion about storing dissolved CO2 in this fluid to combine geothermy and carbon sequestration?
Okay, thanks Ellen. Thanks, Simon, for the question. I think in terms of which fluids could be used to store energy, the options are you could store thermal energy in groundwaters, so that would be water. You could store mechanical energy, you can store mechanical energy in terms of air as a fluid, so you can compress the air that I mentioned, and you can also store chemical energy in terms of things like methane or hydrogen. So there's different ways of storing energy in the subsurface: mechanical, thermal, and chemical. Whether or not they could be linked with CO2 storage, I think is more of a difficult question.
Yeah.
I don't know if Max, if you could.
Yeah, so I'm aware from research that's been done in Switzerland, this isn't being considered, Sam, in the UK, to the best of my knowledge, unless Ed knows better. But CO2 has been considered as a medium in geothermal, so to gain heat from the subsurface, not using mine water, as Ed is indicating, but it has been using CO2 as a medium to transfer the geothermal energy. But it's not something that we are considering that I know of in the UK.
Great. We'll move on to a question from Sam. He says, thanks for the interesting talk. Are there any risks or barriers associated with hydrogen use as a fuel that may prevent its widespread use in the future?
Yeah, I could make a start with the question. So thanks, Sam, for the question. In terms of hydrogen storage, hydrogen can embrittle steel, so you can get brittle failure of steel if the steel is for example, from an old borehole completion or casing. So there would need to be an assessment of whether or not any old boreholes intersect your storage complex. There are regulations in place for use of hydrogen in domestic use as a blend with natural gas. In terms of subsurface storage, again, there could be risks from leakage, although it's useful to point out that there have been no documented examples of leakage from a storage cavern itself. There have been leakages from the boreholes connecting the surface to the cavern, but not from the cavern itself in terms of halite cavern storage. There is a potential for reactions in porous storage, so that's storage of hydrogen in sandstones in terms of geochemistry or in terms of microbial activity. And both of those could either affect the quality of the hydrogen that could be extracted from the storage medium, or indeed affect the performance of the reservoir itself. And in terms of, there are commercial risks as well in association with retrieval of stored product. So yeah, there are several risks. This falls into the remit of the work that the IEA have been looking at on underground hydrogen storage, and I'd link back to the reports from the International Energy Authority on underground hydrogen storage that I mentioned previously. And that gives a good review of current understanding on that.
Thank you. A question for Maxine now. This is a question from Chris, who says, maybe a silly question, there's no such thing, but how well contained are CO2 storage sites? For instance, how likely is CO2 to escape some of these storage sites through some kind of geological movement or diffusion stroke bleed out?
Okay, it's not a silly question at all, Chris. It's a very good one. And this is part of the work when we are talking about management. I've mentioned management several times, but how we would manage what we were doing in the subsurface is to ensure that the examples that you give, there might be geological or movement. This is exactly the type of work that we do as a geological survey for commercial projects. They do the same thing for their own projects. They look at what the maximum pressure is. We looked earlier on in some of the slides that I'd shown you how this pressure of injection might cause an increase in the reservoir pressure. And so we understand, so we have the benefit of many years of hydrocarbon production, both gas and oil, for us to understand the character of the geological formations, whether they're fields or they're host formations. And we can have a look at the maximum limits, and then we put a safety factor on it, and then we simulate it, and then you compare it with oil and gas exploration production figures. And so individually, projects look at those very carefully and make sure that they fall within the pressure limits. And for us as a geological survey, we look at the regional picture. So there's illustrations that I showed earlier to say, well, if there's more than one project in a sandstone, what happens if there's a cumulative effect? And we then examine the character of the boundaries or not between projects to ensure that this very careful management of the subsurface maintains it securely in the subsurface. And we have the benefit of decades of the experience from the oil and gas sector. And we can not only use their experience and their data and their knowledge to be able to ensure that there should be no geological movement, there will be no geological movement, and to ensure that the CO2 stays securely in the subsurface.
Thank you, Maxine. So a question for Ed, actually two questions from Paul. Which countries are seen as a leader in new storage technologies? And also building on the theme of leakage, how much are we looking at that? And does this risk reducing future investments?
Yeah, thanks, Paul, for the questions. First of all, thinking about areas, countries which might be leaders in different technologies. So the geology, not just the geology in the UK, but the geology between different countries is different. So different countries can support, the geology of different countries can support different technologies. So not all technologies could be sort of deployed and supported everywhere. However, we've got a really good track record globally in underground gas storage, that's storage of methane in caverns. So this has been operating since the 1960s in different places. And this gives us a really good evidence base on understanding sort of cavern performance. Underground gas storage is carried out in several areas in the world. So the UK has several facilities, places like Northwest Europe, so France, Germany, Poland, Netherlands. Thinking just about hydrogen storage, there are only 2 locations in the world that have operational cavern storage of hydrogen, and that is at Teesside in the UK and also Texas. So that those could be considered sort of leaders in underground hydrogen storage in caverns. Thinking about compressed air energy, there's only been a couple of pilot projects in the world. One is in Hough in Germany. And there's also Macintosh in Alabama in the US. And then looking at the thermal storage, looking at aquifer thermal, as I mentioned, the Netherlands is head and shoulders above in terms of schemes that are operational, but there are also operational schemes in, for example, Denmark, Sweden, UK's got a couple of schemes. So there are schemes, and there are areas that could be used to sort of learn from. And just remind what the second part of the question was, Ailey?
It was how much are we looking at leakage, and does this risk reducing future investments?
I think, as I said previously, leakage from a cavern itself hasn't been reported, but there have been incidents where there's been leakage from boreholes that connect caverns to the surface. So that would be one area to look at. Leakage from porous strata. So if we're looking at using depleted gas fields, these are areas of there could be sandstones that have in the past contained natural gas. So there is work underway to understand the conditions where the conditions that would need to be met for those to either contain or not hydrogen. So in terms of leakage, there are processes or risk assessments that can be done to understand that. But it might be a consideration in some scenarios, but there'd be research that could be carried out to address that question.
Thank you. We've got 2 interesting questions here in a slightly different theme, looking at skills. One from an anonymous attendee: are there technical geoscience skills that are required for this emerging area that are not already used or focused on in traditional geoscience industries such as oil and gas? And another similar question from Corey: how would a geology graduate get involved or work on subsurface hydrogen or CO2 storage in the UK? Would you like to take that one to start off with, Max?
Yeah. I'm looking for the question. Sorry, Ailey, I'm looking for the question.
That's okay. So are there technical geoscience skills that are required for this area that are not already used in traditional oil and gas industries? And how can a graduate get involved in these areas?
Okay, so it's very much the using the sort of skills that have been developed in the past on the experience of oil and gas, but really, but technically it is slightly different. So it is adapting the skills that have been developed in the past. Of course, we are injecting rather than producing. So there will be skills that are needed in terms of the reservoir. We are concerned that we are not have enough people coming into our industry who see perhaps the end of a hydrocarbon extraction activity. There will be an overlap, of course, but we need the skills. So, to the best of my knowledge, the skills are, as we have understood previously, both the practical and the geoscience and the interpretation and the sort of engineering skills, but these are not quite the same as in the operations themselves are a little different. So in terms of how do you get into it, there are several courses on CO2 capture and storage that are run by universities. There's one I know, I'm based in Edinburgh, and there's one based at University of Edinburgh, but there are other university courses as well. So in answer to your question, yes, please do. Please do engage where you can. You know, if you wish to then engage in any of these postgraduate educations, the opportunities, and I'm not aware that there are any different skills. There are, however, there'll be adaptation and different use of the skills that we have already learned.
I'll just add in there that BGS does take graduates as well, and we'll be running an open call each year as well. Okay, a question for Ed around fractures and their influence on flow through sandstone. So this is from Mark, and he says that fractures do influence flow through sandstones. GS and I are looking at this in the Sherwood sandstone in Northern Ireland. What work are BGS doing to characterize such structures?
Yeah, thanks, Mark, for the question. When looking at thermal storage in aquifers and potential for fracture flow in sandstones, we will be using the UK Geoenergy Observatory at Cheshire that I described, which is a series of boreholes accessing the Sherwood sandstone as well. And in those boreholes, we will be carrying out thermal trace and thermal response tests in the boreholes. So essentially, we'll be heating up the borehole and then monitoring the thermal plumes away from those boreholes. So what we anticipate to see will be faster and further migration of heat along fractures, and then more of a contained migration of heat closer to boreholes. So that's one of the ways that we'll be looking at potential for fracture flow in the shallower parts of the Sherwood sandstone. Thanks.
Great, a question for Maxine then. This is from Glyn. Where in the UK is the UK CO2 storage research facility likely to be based? And are BGS aware of the work conducted by CO2 CRC in Otway in Australia?
So thank you, Glyn. Yes, we are very much aware of the CO2 storage facility in Australia. So I'd mentioned that we are building the science case, and our science case has been engaging our stakeholders. We've got to say it was a big thank you to all of the pilot sites, the research sites around the world who have been very helpful, including CO2 CRC in Otway, Australia. So looking at what they do and what we are proposing, their site injects a mixture of gases. It doesn't just include CO2. And we are then looking at how we can work in a complementary way. So their work is onshore. Our UK plans are for storage offshore, so the monitoring technologies will be different. And so, yes, we have taken account of all of the pilot sites around the world, and big thank you to everybody who was so cooperative and helpful. So it is likely to be based, in terms of a CO2 storage research facility, it is likely to be based in those strata that are planned for CO2 storage by UK commercial projects. And as we have seen, the commercial projects for, say, Teesside and Humberside, or for HyNet in Liverpool Bay, and they are both based in Northern England. And so that is where the facility is more likely to be based.
Thank you. Okay, a question for Ed on storage cavern formations. This is from Chris. Can the storage cavern formations withstand the magnitude of pressures from hydrogen or compressed air? And what technologies will be used to monitor for faults in the cavern formations?
Yeah, thanks, Chris, for the question. So we're lucky with cavern storage in that we have as I mentioned, we have a long, or globally, we have a long history of cavern storage dating back to 1960s, and this gives us a really good understanding of some of the mechanical and engineering parameters that allow safe storage. So, for example, as a rule of thumb, and this would be then applied individually at different schemes depending on the local geology, but as a rule of thumb, the schemes would have a maximum storage pressure of 80% of the lithostatic pressure. So that's the pressure of the rocks above. So you wouldn't want to exceed 80% of the lithostatic pressure as a rule of thumb. And this means that you would typically avoid any fracturing of the rock or any potential for gas to escape through halite. However, there definitely are questions about whether or not storage of hydrogen would operate at timescales that are shorter than seasonal. So would we be looking at the potential for higher storage pressures and higher rates of withdrawal and injection? And those are areas that are areas of current research, looking at the behavior of rock salt at those different mechanical conditions.
Thank you. A question for Maxine from Rochelle. When you're mapping and modelling the fault boundaries in the Bunter Sandstone to consider if the boundaries are open or closed, do you plan to consider the future impacts of climate change, i.e. overburden pressure from glaciation, and how this may impact fluid flow?
Okay, one of the things I think we've got to consider there is timescale. So when you consider the planning and modelling of CO2 storage, injection and storage, you would then have to consider how long it would take in terms of the trapping mechanisms. So one of the main characteristics, and you all know this, I don't know whether you drink Coca-Cola, tonic water or champagne, you will know that CO2 goes into solution under pressure. Pick your one. So one of the main trapping mechanisms for CO2 after injection is that it dissolves extremely quickly under pressure. So in terms of, it is very, very rapid, but both in real time and in terms of geological time. And then we look to see how much the character of the stored CO2 changes over time scales. And our objective then is to see over tens of years, hundreds of years, and thousands of years to see what happens to the CO2. So the CO2 would initially, it would dissolve, some of the buoyant gas would rise upwards, some of the gas is trapped between the pores, as residual trapping, and some of it remains as free gas. But our modelling shows that the free gas, the gas cap, gradually decreases over periods of a few thousand years. So in terms of the impacts of climate change, and your indication here is overburden pressure from glaciation. By looking at the past, we have seen that glaciation takes place over not just thousands of years, but tens of thousands of years. So in terms of the timescales, the stored CO2 would either be in terms of dissolved, or it would eventually form minerals, calcite minerals within the pores within the rock. So it's a timescale difference. However, you are right, we have thought of this, the impacts of climate change into the overburden pressure from glaciation, and also the paths to overburden pressure retaining from glaciation. And I believe in part there is a project called the SHARP project, which is investigating some aspects of this work, but there is quite a disparity, Rochelle, in terms of the timescales.
Thank you, Maxine. A question for Ed. Is formation of scale or corrosion due to salts a problem for heat storage when using water circulated into the subsurface?
Okay, thanks for the question. I think that for the aquifer thermal energy systems that I've been talking about, we're talking about very low enthalpy, so low changes in actual temperature. So I can't think of any instances where salt corrosion has been an issue at those temperatures. It could potentially be more of an issue at the higher temperatures, or the hotter, drier rock temperatures, but that's not an area of my expertise, so I wouldn't be comfortable commenting on it. But yeah, so I won't say no, but certainly at the lower temperatures, I wouldn't think that's one of the main considerations there. Thanks.
Great. Another question, I think, for you here, Ed. The IEA Hydrogen TCP Task 42 UHS report, it's that title, provides an overview of the TRLs for different UHS technologies. Fast cyclic salt caverns are shown to have a TRL of 5 to 6. What are your views of the potential challenges of fast cycling salt caverns in UK environments? And do you see this solution developing to a TRL 9 to 11, which is a commercial operation or maturity in the near future?
Yeah, thanks for the question. That refers back to the International Energy Agency report that I was mentioned previously. So I think that the challenges for fast cycling caverns will be firstly whether or not the geology provides a barrier to that. So can caverns be located at particular depths that can, with the mechanical envelope that can support fast cycling without failure of the cavern walls? So that's really a point that could be modelled. We could look at modelling that. However, it's probably more of a technical challenge, whether or not we can have compressors that can carry out fast cycling at that sort of cavern sort of scale. And also the economics, have we got our rock salt in the right areas to support the sort of demand if fast cycling is required? So I think that there is potential. There are some questions which will need to be addressed, but it's definitely, operating caverns in a different way is definitely something that more than one research group is looking at the moment. So thanks.
Thank you. Another question for Maxine. This is similar to some questions we've had about leakage. So in a porous medium like sandstone, what's the likely leakage of CO2 and therefore the likely danger of effectively turning the North Sea into a big carbonic acid sink? But then also a second part of this question, how would you mitigate against shortcuts taken by companies in the interest of profits or just getting ahead in the market in the future that put the climate at risk and the geological safety of the seabed at risk? So any thoughts on regulation there?
Okay, so one of the things at the moment, of course, is that with more CO2 in the air, this is increasing. This is not a geology research issue. This is sort of a general concern, is that there's more CO2 in the air and it is causing ocean acidification anyway. So in terms of our concern, our important part is to make sure that it does not leak. So this is where it's very carefully looking at the subsurface. Now you mentioned in your question that you're turning the North Sea into a big carbonic acid sink. So what we're looking at is the groundwater in the subsurface at least 800 meters beneath the seabed. So one of the activities then is to make sure that it stays in the subsurface, as oil and gas have done for million geological timescales, millions of years. So it is not to make it leak to the CO2. So one of the questions I'd answered earlier on is that what happens to the CO2? So the CO2 does go into solution, as in a fizzy drink, and there's the brine. So it's all very in at depths. At groundwater at depths is not drinkable water. It's very salty or brine. And so what happens is when the CO2 dissolves in the brine at depths greater than or much greater than, say, 800 or 1,000 meters beneath the subsurface, the brine becomes more dense. And so the dense brine containing the CO2 sinks down rather than upwards. So this is a sort of a modeling and then eventually modeling activity for us as geology, as scientists, and eventually it precipitates as minerals. So in part, in terms of leakage, this is very important from both companies and from us as the sort of representatives of the public for public science, that the CO2 does not leak. That is the main objective of our work. And then I'm trying to think of the answer of the question for how would you mitigate shortcuts taken by companies? Well, I would say that part of the regulation that is set in the legislation, initially by the EU Storage Directive, but also as transposed into UK law, is that the monitoring of these storage sites and the careful consideration of mitigating activities and corrective measures, if there's any indication that these stores are not operating as they should do, then that is the regulator's job to enforce that very, very careful and very thorough monitoring of conformance of operation. So I believe that there is sufficient regulation in the UK to ensure that there are no such things as shortcuts taken by companies. In part, one of the objectives is to demonstrate to the regulator that the store is operating, that it is perfectly and it is well contained and is securely held in the subsurface, because they cannot they cannot close the site until they are able to demonstrate that clearly to the regulator. So I don't think that we're putting the seabed at risk by considering carefully our subsurface operations, monitoring and conformance of those operations.
Thank you. A question related to that in terms of regulation. Has regulation kept up with carbon storage developments, and who are the key parties involved in regulating the sector? Okay, so in answer to that question, we work very closely with the regulators. So you may be aware, or you may perhaps not. So one of the maps that I showed you earlier in my talk was that there are areas identified for CO2 storage. Now, the UK is the first country to do this. The first one was the first CO2 storage licensing round. Previously, we've been with oil and hydrocarbon, oil and gas licensing rounds. Now, the North Sea Transition Authority now have CO2 storage licensing rounds. They work, BGS, the Geological Survey, works very closely with the North Sea Transition Authority. So in terms of, has the regulation kept up with storage developments? Yes, I believe it has. In terms of that aspect, are the key aspects of the key parties involved. So that would be mostly the North Sea Transition Authority, but it would also be working with the Crown Estate Scotland or the Crown Estate. And then you would also be looking for those onshore parts of your project. That would be the Environment Agency. And also you would have to consider the Marine Management Organisation and very importantly, of course, the Health and Safety Executive. So I think there's a wealth, and that's just, there are more regulators that are involved. That's just the sort of key ones. So I hope that helps you with your key parties involved in regulation. Thank you. Okay, another question on CO2 storage for you, Maxine, which they say may be another silly question. Definitely not. But perhaps, I guess this is to a wider public audience, perhaps they need a reassurance that pressured CO2 storage is not going to lead to the same effects as fracking for gas. So can we be sure of this? Okay, one of the things that we had mentioned earlier was the sort of modelling of pressure of injection. And we'd also then, as Ed has said, both for hydrogen and for CO2 storage, establishing clear limits of what the maximum pressure should be. So when you have fracking, that's when the pressure has been exceeded. And so we keep, as Ed says, within certain limits, accepted limits, and then with safety factors to ensure that there should not be any fracturing, and the modelling that we showed you earlier on. I've mentioned earlier on about the conformance, monitoring for conformance, and conformance of seismicity. So using microseismometers to demonstrate that there should not be microseismic events that might indicate that fracturing. I wouldn't call it fracking. I would say we wouldn't ignore what I say at fracturing, is to make sure that there should be none of that sort of seismic activity takes place, that we stay within the acceptable limits within the established for each individual site, which are individual, which is set individually on the characteristics of the rocks and the existing as Ed has described, the lithostatic pressure. Sorry. Hope that is a little bit reassuring. Great. Okay, so we've got 10 minutes left and we've got 10 open questions. So let's see if we can get through those. So on a slightly different topic, where does the long-term liability of CO2 storage sit? Okay, this is very straightforward. So in terms of the sort of conformance for monitoring, when the operator has reassured the national regulatory authorities that after they've completed their storage operations, after sufficient time with there is of monitoring equipment to demonstrate that the store is operating, is performing in the way that they have predicted, only then will that be handed over to what's called the competent authority. So that will be the appropriate government department. I mean, this is so far in the future, I'm not sure that one has been identified, but nevertheless, it will be taken over by the government. And you say, isn't this
you know, isn't this new? No, it definitely isn't. For example, this is where the role of where coal mines, the ownership of coal mines has, for example, been taken over by the Coal Authority. So that is where when the site has been demonstrating as being completely safe, stable, and suitable to be completely closed, then that liability then will go on to the competent authority, which will be a UK government department.
Thank you. Okay, 2 questions from Mark here. We've talked about lots of storage, offshore storage potential in the UK, but what about onshore? And also, is BGS looking at CCS through rock mineralization, particularly in basalts or other igneous rocks?
Okay, so we know our offshore storage potential from the data sets and the knowledge that we have from the oil and gas industry. So in terms of the subsurface, we know the subsurface offshore where it has been used for oil and gas production far better than we know it onshore because of the very detailed seismic data sets. Also, because of the character of the rocks themselves. On the whole, the rocks offshore tend to be younger, more porous, and less faulted. So they're more of an attractive proposition than for storage, than sort of the older, more fractured rocks. There is still the possibility of storing them onshore. It's not something that we've assessed. However, the question is being asked because if somebody is isolated from the coast and they have a CO2 storage source and they are away from another project, then somebody is of interest. I'm not sure that the legislation has completely gone through. So we were talking about the regulatory requirements and the regulators that are assigned. Talking to the regulators, I'm not sure that the regulatory steps have all been completely closed in terms of making a sequence of the regulations that an operator might follow. So there is storage potential onshore, but for the most part, it is not at the scale of the storage capacities, nor at the rates of which we can do injection that we need to do to meet net zero. We saw that map. That's got sort of millions of tons per year from each one of those industrial clusters. We've got to think big and act big. But in the future, perhaps, where we are looking to those hard to reduce sources that are isolated, perhaps we would use onshore sites. And then I think you've got another.
Can I just add to that?
Yeah, go away, Ed. Go ahead.
I think it's quite interesting, and it's quite useful to actually contrast CO2 storage, which is permanent or should be permanent, with energy storage, which is temporary. And it might mean that, you know, some of the more remote locations that are offshore might be less suited for energy storage. And some of the more onshore sources of storage, which might be located closer to sites of demand, might be better suited for temporary energy storage. So thinking about, you know, demand really is quite a useful way of trying to understand where storage might be needed.
And so the second part, I think there was a second part of the question. So so to Mark here, so is BGS looking at carbon capture and storage through rock mineralization, particularly in basalts? So we are well aware from the Carbfix project in Iceland of the characteristics of the rocks that they are doing. So they're going straight to rock mineralization. It is relatively small scale. It's in the hundreds to thousands of tons per year. But we are looking to use the rocks that we have, and in the question that Mark has as well. But the Icelanders, they have plenty of very fresh basalts. They're very, very, very new in terms of geological terms, very new indeed. And so they're quite reactive to the carbon dioxide that's inserted in the sort of fractures and the buggy paces that are within the basalts. So the BGS mapping work will have mapped basaltic rocks and other basic igneous rocks all around the UK. But Mark, they don't offer the same attractiveness in terms of the size and the scale of CO2 storage by mineralization. Also, for the most part, the UK basaltic rocks tend to be quite a bit older. Even the sort of tertiary provinces in the sort of the outer isles and the western part of Scotland. But for the most part, basaltic rocks of Carboniferous age tend to be a lot more weathered already. They would have been a lot more fractured. They're less confined. They are less of a prospect. When speaking to an operator who does this, and they said, oh, well, you know, you would just use your freshest, youngest rocks possible to use basaltic rocks for storage. So we would tend to favour the ones with the biggest impact. So and as we have the benefit of those, and they are offshore and in porous strata. So it's picking our best rather than having to go to basaltic rocks, unless you want to say something, Ed, there.
No, that's nothing to add.
Okay, great, we've got just a couple minutes left, so we'll see if we can get through some more questions. This is a question from Ian. He says, you highlight how the seabed could become very crowded with the co-location of offshore wind and storage. This could present a potential challenge to MMV plans. Is there any ongoing research considering existing and new technologies which would allow co-location?
Shall I pick that up, Aileen? Okay.
Yes.
Yes. Okay. So this is a lovely question, and yes, there's a lot of interest and a lot of research. So so when you say it's crowded, and so to some extent it sounds a bit sort of odd, doesn't it? That large area offshore, but the extent of geological formations suitable for storage, they are very large. Similarly, wind farms are similarly large. So there's plenty of concern for co-location, but also then it's an interesting challenge. And so there are many research activities considering how this might be done. So clearly you can't do towed seismic surveys weaving in and out of wind farm pylons, but perhaps you can then look at using techniques that use the wind the wind turbines as a source of sound, or to do your seismic surveys instead, or you would do seismic surveys that do not require shipping to be able to tow a seismic source and seismic streamers behind them. So it's a really, really interesting challenge. Lots of people are looking at it, particularly things like downhole monitoring using fiber optic cables. So these are, you can look at temperature, you can look at strain, and pressure. So we're looking at these as well, and also deploying arrays on the seabed and in the vicinity of injection wells that we would use for monitoring for conformance, with hopefully minimizing the conflict of use, but better still, and with synergies of use, so enable co-location of both wind farms and storage sites offshore. So yes, it's a lovely question, and yes, there's an awful lot of interest in research groups around the UK and around and globally as well.
Okay, a question about collaboration here. We've got just 2 minutes, so we'll see if we can get 2 questions in. Are we getting reasonably effective collaboration, cooperation, synergies, cost sharings, etc., with Europe on hydrogen and CCUS? Ed, would you be able to take that?
Yeah, I think in a nutshell, we probably are. We have active, we're active in research projects which are funded by the EC and we have very good relationships with different partners across Europe. So I'd say yes, definitely.
That's great.
So I can also say, yeah, so some of the projects that I haven't been able to summarize today were funded by the EC. So for example, some of the work that we have done on industrial source carbon capture and storage was led by the Netherlands, of which UK was part, and we've been looking at hydrogen and CO2 storage in a project that was led by Norway, and so on and so on. So we have had an awful lot of effective collaboration and cooperation and sharing, both with sort of CO2 storage and also for hydrogen as well.
Thank you. Okay, just one final question. Deployed large-scale installations are required on a timescale of less than 5 years. How closely are industry involved in planning and system design to achieve this, and in estimating costs? Maxine?
Okay, so industry are looking very much to be able to look at the effects, the benefits on the projects they already run. We've mentioned 2 projects in the North Sea already, well, mentioned one anyways, one at two are in Norway. There are one in development, more than one in developed in the Netherlands. And so what we're looking to is to say how can we benefit from that? So industry, for example, the 2 storage projects in Norway are both industry-led. The Norwegian approach is one that is commercial projects, and their government then is supports research. So industry are very close, where there is nevertheless research that industry cannot do. So I mentioned the CO2 storage research facility, and they have been very cooperative with us to say these are things we cannot do because they'll compromise our commercial activities. But could you do it? And so yes, industry is working very closely to be able to deploy these large-scale projects. But we do need to deploy them at pace and at scale if we're going to be able to achieve net zero for the UK.
That's great. Thank you very much. That brings us to the end of our session today. Thank you, Maxine and Ed, for your very thought-provoking presentations. And thank you, everybody, for joining us and for all of your great questions. There are more webinars taking place throughout the week for Net Zero Week. If you visit netzeroweek.com/business, you can get involved there. Thank you very much.